Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow. But there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles, predicted by physics but never observed, might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures: long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper 3-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life, or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice, or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds, as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Hycean worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Hycean worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favourable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Hycean worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, 0.60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighbouring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy, each type presenting unique challenges and opportunities for life, each potentially harbouring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. How the moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years, governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the moon was recognised in ancient times, but understanding exactly how the moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the moon. The water at this location is about 4,000 miles closer to the moon than Earth's centre. The moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the moon that's about 7% stronger than the pull experienced by Earth's centre. This differential force pulls the ocean away from Earth's centre, creating a bulge of water on the moon-facing side. Now consider the opposite side of Earth, the point farthest from the moon. Here the ocean is about 4,000 miles farther from the moon than Earth's centre. The gravitational pull from the moon at this location is about 7% weaker than at Earth's centre. Earth's centre is being pulled toward the moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through 2 high tides and 2 low tides each day, though not exactly every 12 hours, because the moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the moon's gravitational pull, perhaps a foot or two in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the moon and sun. The sun also creates tides on Earth, though they're smaller than lunar tides despite the sun's vastly greater mass. The reason is distance. The sun is about 400 times farther from Earth than the moon, and tidal forces depend not just on mass, but on how much the gravitational pull varies across Earth's diameter. The sun's great distance means its gravitational pull varies less across Earth than the moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the moon and sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high tides and especially low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the moon and sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the moon is overhead or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the moon by Apollo astronauts have confirmed that the moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the moon formed, likely from debris created when a Mars-sized object collided with the young Earth, the moon has moved substantially farther from Earth. Early in Earth's history, when the moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. the moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the moon is an example of tidal locking in progress. The moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the moon, and the moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies and how the Moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances, and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties, like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass, for the smallest red dwarfs, up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated, but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained, by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously, The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our Sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our Sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected. the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has 2 protons and 1 neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, 2 helium-3 nuclei collide and fuse, forming ordinary helium-4, which has 2 protons and 2 neutrons, and releasing 2 protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into 1 helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1 million times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. The extreme environments where life could thrive, Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure, at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Baraful's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web, this mysterious substance which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light-years across, and stretching for hundreds of millions of light-years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions a billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich, structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern.